This video is about the magnitude and direction of vectors. To work with a vector, we need to be able to find its magnitude and direction. Magnitude is denoted using the following symbol: two straight bars with an italicized lowercase letter inside. As shown, we have V. And we find the magnitude using the Pythagorean theorem or the distance formula, remembering that the Pythagorean theorem is a squared plus b squared equals c squared, or as we like to say in trigonometry, opposite squared plus adjacent squared equals the hypotenuse squared on a right triangle. And the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared, where x2 and y2 and x1 and y1 come from coordinate pairs, like so. And to find the direction of a vector, we use the inverse tangent function. So we have the tangent of some angle theta equals b over a, which implies that the angle theta equals the inverse tangent of b over a. And again, remembering here that our tangent is our opposite over adjacent. When we're working with a right triangle, we have our hypotenuse. If this is our angle theta, over here is opposite, and here is adjacent. And two vectors are considered equal if they have the same magnitude and direction, or if they have the same position vector. Position vectors are discussed in video 1. Here's an example to find the magnitude and direction. Starting here with a position vector, A, B. Remembering position vectors always start at the origin and are called by their terminal point. And we can see in this illustration where exactly the angle theta is located. And we're working in quadrant 1 here. And angle theta is formed between the x and the y-axis by the vector. So using some points to start filling in some of this information in finding magnitude and direction. Starting here with initial point P negative 8, 1, and terminal point Q negative 2, negative 5. So we can graph this vector over here. We don't quite have enough room for it, but we would go 6, 7, negative 8, up 1. That's our point, negative 8, 1. And the terminal point is negative 2, negative 5, so negative 2, and then down 5. Line segment connecting these guys, and an arrow to indicate the terminal point. We have to be working with our position vector, shown in this diagram in blue right here, and called u. Remember, to find the position vector, we take second x-coordinate minus the first x-coordinate and the second y-coordinate minus the first to get that terminal point and the name of our position vector. So here we have a terminal point negative 2 minus initial negative 8, comma, we look at the y's, negative 5 and positive 1, so minus positive 1, giving us negative 2 minus negative 8. A negative and a negative is a plus, so that's negative 2 plus 8 for our x's, and we have negative 5 minus positive 1, or negative 5 minus 1 for the y's, further reducing it to 6, comma, negative 6, and that is our position vector. So we go ahead and draw that. And it's here for us already, but just remember the position vector always starts at 0, 0, And we have this point here, 6, negative 6. We'd go over to 6 on the x and down on the y. Now we have the position vector. The second step is to use the Pythagorean theorem to find the magnitude of u. So here we have the magnitude of u is the square root of x squared plus y squared. So let's take a look at what this looks like here. So I'm going to make my right triangle. Here's that right angle. Here's u is the hypotenuse, and here's x and y. So if the formula is side x squared plus side y squared equals hypotenuse squared, that gives me x squared plus y squared equals my hypotenuse squared. I square root both sides, and that's where that square root x squared plus y squared is coming from. And this goes away, and we just have hypotenuse. In this case, the hypotenuse is the vector u. And we just go ahead and plug in that information. We have 6, the units on the x, and 6 units on the y. So we have 6 squared plus negative 6 squared equals the square root of 36 plus 36 is 72, further reducing to 6 root 2. And that is the magnitude of the vector u. Now we find that theta using the inverse tangent function. So remembering theta is the inverse tangent of b over a. So here we have a and b, which we've been calling x and y, and we plug in again. So we have theta equals inverse tangent negative 6 over 6, which is what we would hit in our calculator. We'd hit the inverse tangent button, and then we'd have negative 6 over 6, which gives us the inverse tangent of negative 1. And if you're set in degrees, your calculator will give you 45 degrees. And if you're set in radians, you will get your answer in radians. Next example, showing that a vector v with initial point 5, negative 3, and terminal point negative 1, 2 is equal to vector u with initial point negative 1, negative 3, and terminal point negative 7, negative 2. First thing, draw a picture. We'll draw our vector v first. Initial point 5, negative 3, so that's over 5 on the x and down 3 on the y. Terminal point negative 1, 2, negative 1 on the x, up 2 on the y. And we can see our vector v right here in green. Drawing vector u, initial point negative 1, 2, 3. Terminal point negative 7, 2, over to negative 7, up to 2. And here we have that vector u drawn in space for us. So remembering that two vectors are equal only if they have the same magnitude and direction, or if they both have the same position vector. For this problem, let's calculate the position vector for both and see if they're equal. Starting with v, we have our x2, negative 1, minus our x1, which is 5. Our y2, 2, minus our y1, negative 3, giving us negative 1 minus 5 for the x's, and 2 minus negative 3, a minus and a minus makes a plus, so we have 2 plus 3 for our y's. Further simplifying to negative 6, 5. Working now with u. U has an x2 of negative 7 minus x1, negative 1. To the y's has a y2 of 2, a y1 of negative 3, giving us negative 7 plus 1 for our x's, and 2 plus 3 for our y's, which can be simplified to -6, 5. Because both v and u have the same position vector, we can conclude that they are equal.